Hello and welcome to Set Theory, a bite-sized lecture series. In these videos, you'll get a conceptual overview of set theory that doesn't take all day. If you're new to this channel, be sure to check out the playlist with all the videos in this series, which I'll link to in a card in the corner of the screen. The last 2 weeks have been a lot of definitions and theorems, but this week is finally going to be a little more conceptual. Today we're going to learn about relations. But first, we actually have to define one more thing: an ordered pair. The most straightforward example of an ordered pair is a coordinate on the Cartesian plane, xy. Xy is a pair of numbers, x and y, and that pair has a fixed order. If you switched x and y to get yx, that would be an entirely different point. As we do in set theory, we're going to formalize this intuitive definition into something that we can do lots of complicated math with. We're going to say that an ordered pair xy is the same as the set of x and the set of xy. What we're doing here is saying, here are our two coordinates, x and y. We don't know what order they're in, but this is the realm of stuff we're going to pick from. Then we say, now here's a set with only our first coordinate, x. Now we know the first coordinate is x, and since our realm of stuff is x and y, the second coordinate has to be y. So it's sort of just a roundabout way of figuring out what order these two elements are supposed to be in. Now that we got that out of the way, let's talk about relations. You've probably learned about functions before, and you may have even seen something like this, where these blobs are the domain and range of the function, and each input goes to at most one output. Well, relations are a similar concept, except there isn't really an input variable and a distinct output variable. It's more like the two variables are on opposite sides of a relationship that could either be true or false. That's kind of confusing, so let's look at an example. Take the set 2, 3, 5, and the relation less than. We can draw this sort of diagram thing, illustrating all the relationships between pairs of numbers in the set. 2 is less than 3, 2 is less than 5, and 3 is less than 5. Another way to think about this is that there are a bunch of possible ordered pairs of the numbers 2, 3, and 5. There's 2, 2, 3, 2, 5, 3, etc. Each of these ordered pairs can be translated into a statement using the relation 2 is less than 2, 3 is less than 2, and 5 is less than 3 respectively. Obviously, none of these statements are true. The only ordered pairs that fulfill the relation are the ones in the diagram: 2, 3, 2, 5, and 3, 5. So we're going to write our relation like this. R equals the set of the ordered pairs 2, 3, 2, 5, and 3, 5. Using our definition of ordered pairs, we could also write R equals the set of the set of the set of 2, and the set of 2 and 3, and the set of, you get the idea. But we would never actually write it like this for obvious reasons, except to prove something specific about R. There's a problem in the example problems that deals with the union of R, in which case we would want to use this definition. A general way to write R for some relation would be R equals the set of ordered pairs xy such that x and y fulfill the relation. But what even are x and y? With functions, we can say x is all real numbers from negative infinity to infinity, or whatever our domain is. But sets are much more abstract. Our relation could be the set of ordered pairs of cats x and y such that cat x is much cuter than cat y. What we have to do is define a domain and range for the relation. Domain being everything x could be, and range being everything y could be. A more formal way to say this is the domain of R is the set of all x for which there exists some y such that xy is in R. Using our example from before with 2, 3, and 5, 2 and 3 would be in the domain, but 5 wouldn't be, because it isn't less than any of the other numbers in the set. Similarly, the range of R is a set of all y for which there exists some x such that xy is in R. Using the example, 3 and 5 would be in the range, but 2 wouldn't. Finally, the field of R is defined as the union of the domain of R and the range of R. That is, it's everything that could be on either side of the relation. In the example, that would simply be the set 2, 3, 5. Another way to think about the domain and range of R is through something called the Cartesian Product. Let's say the domain of R is the set A, and the range of R is the set B. The Cartesian product A times B is the set of all ordered pairs x, y, such that x is in A and y is in B. And the reason this is called the Cartesian product is because we can draw it on the Cartesian plane. If this range on the x-axis is A, and this range on the y-axis is B, the Cartesian product is this rectangular area, where x is somewhere in A and y is somewhere in B. And now we start to see how relations and functions and those equations that aren't technically functions overlap. Take the circle x squared plus y squared equals 25, for example. This isn't a function, but it is an algebraic relation between x and y. The domain of this circle is negative 5, 5, and the range is also negative 5, 5. The relation itself is the set of all the points that make up this circle. And the field is actually this square circumscribed around the circle, where x is somewhere in the domain and y is somewhere in the range. We're not actually going to use algebraic functions and relations that much in set theory, but it's really helpful to understand the concepts behind these things, and we're going to keep using them as examples for all these things. Next week, we're going to specifically look at functions in set theory, so definitely go watch that next if I've posted it already. The last thing to note is that just like functions in algebra, we can extend these relations to however many variables we want. First, we define an ordered triple x, y, z to be the ordered pair of x and y, comma z. In fully expanded set notation, that would be the set of x, the set of x, y, and the set of x, y, and z. So for every ordered set, in order to make the set notation for it, we just start with the first component, then add the second component, and so on and so forth until we have all the components. Once we've done this, we can form relations between groups of 3, 4, or even infinity coordinates. For example, we might have r equals the set of all x, y, z, such that x is less than y is less than z. In our previous example, the ordered set 2, 3, 5 would be in R, but not 2, 5, 3, 3, 5, 2, or any of the other possible orderings of the members of the field of R. And that concludes the 4th video of this video series about set theory. I hope you enjoyed it. Let me know what you think, and if there's anything that would make it better. Also, make sure to check out the example problems in the description. Thanks for watching. See you next week.